Precalc chapter 11, section 1. So we're going to talk about limits. A limit, if f of x becomes arbitrarily close to a unique number L as x approaches c from either side. The limit of f of x as x approaches c is L. So the notation here, the limit as x gets close to c. So as x is getting closer and closer to c for the positive and negative side, then what does the function do? The function will get closer and closer to L. That's what the limit is just saying. So, for example, for this problem here, the limit as x approaches 0. So x is getting closer to 0, so like 3 to 2 to 1 to 0, and from negative 3, negative 2 to negative 1 to 0. If you move in that direction from both sides, what does this function here approach? And so then you can put in some values to actually figure that out. So there are a few ways we look at that. One way is to look at it through a graph. And so if we look at the graph of that function, and we can actually use a table to help us look at the graph, closer and closer to when x is getting closer and closer to 0. So as x is approaching 0 from the right and approaching 0 from the left, what is occurring? And so we can punch in values. Not just values like -1 and 1. I'm talking about values like 1/10 for x and 1/100th for x, or like -100th for x. Values that are really close to 0. What is the graph doing? And then what would the y value be here? And so it appears in the graph 1, 2, 3, 4, 5, 6. It appears that it's approaching 6. So let's plug in 0 for x. We plug 0 in for x in this function. We'd have this, which if I simplify that, that's 0 divided by 3 minus 3, which is 0 over 0, which this is the indeterminate form, so there's no solution. So even though there's no solution at x equals 0, we can still find a limit. And this is where limits become powerful, because even though x does not exist at that value, the limit still does exist. And so at x equals 0, there's no solution, but the limit of that would still equal 6. We get closer and closer to 6. You can look at the same thing with the plugging in our table here. What would the y values be? You should see that's approaching 6 from both sides. So the existence or non-existence of f of x at the x equals c has no bearing on the existence of the limit of the function as x approaches c. And so let's look at these three. If I look at the three, I'll sketch the graph of these three. For this one right here, if I punch in like 1, I get 1. If I punch in -1, I get -1. If I did other values, I would actually find I'd end up with these two horizontal lines. And so this was a little more difficult to figure out what's occurring, because at this point, it doesn't actually have a value at 0, but from the right-hand side, we have the y value approaching 1. The left side, the y is actually approaching negative. 1 over x to the 4th, if I sketch a quick graph of that, it's a rational function that if I put like 1 in for there again, I get 1 out, and -1, I get -1 again. Now, I know this is rational. If I look at my different functions or different values closer to 0, it grows infinitely there, and then it grows to -infinity on this side. So there's the rational equation you get, a rational graph you get from that equation. And so what's occurring at x equals 0? There's no value, but we are approaching a value to positive and negative infinity. So what does that mean? We'll talk about that in a second. The third one here, if I graph this value, and you look at what the graph would look like, if you zoom in, you'd actually see it go up and down like this between two values. And it does like something like this. And so that's called oscillating. These are actually the three cases where there is no limit. These are three possible ways to get no limit. When the limit does not exist, the limit of f of x as x approaches c does not exist if f of x approaches a different number from the right side of c than it approaches from the left. And so as the first example, our two horizontal lines here are approaching a positive 1 and a negative 1. The second one is if the function increases or decreases without bounds, it's approaching negative or positive infinity, then there's no limit. And the third one is if it's oscillating between two fixed values as x approaches c, then there's no limit. These are three ways to get no limit. In other words, you would find a limit. These are the basic limits. So the limit as x approaches c of b, a number, a constant, would just be that constant b. It's not changing. The limit as x approaches c of x is just c, because x will be whatever c is if x equals c. And x to the n would just be c to the n. You just actually find the value. And then same thing with the roots, knowing that c has to be greater than 0. These limits allow us to find the limit just through substitution. And so all we're doing for these is just taking our function f of x and plugging c, whatever we're trying to find the limit of, whatever x is approaching, we just plug c in for x and evaluate, and you'll find the limit. If that value exists, then that is the limit. And so these properties kind of go through that same kind of concept, is that we can find the limit quickly using substitution, and we can use these properties to help us find it as well. So if we know the limit of x as x approaches c of f of x is L, and for g it's k, then if you're trying to find the limit as x approaches c of b times f of x, it's just going to be b times whatever the limit of f of x is, which is L. If you're finding the limit as x approaches c of a summation or a difference between two functions, you just find the limit of each individual one and then add or subtract those. So a lot of this is just common sense. For multiplying them, you would just multiply the two together. For dividing them, you would divide the limits together, but you have to realize that k cannot equal 0 there. And then if you're having a power, it would just be the L to the nth power. And so these are common sense ones, but we will use this when you see this, when you're having two different equations or functions, you can break that up to help you find the limit. So some examples, and then we'll call it good. So the limit as x approaches 2 of x cubed. If you just plug 2 right in and get 2 cubed, find the value 8, then 8 is the limit. If the value exists, you substitute that in there, then that is the limit. And the same thing works with trig. Plug that in, so tangent of 3 pi fourths. So you figure what quadrant we're at, 3 pi fourths is here, and so we're at -1. Polynomials and rational functions, it still is occurring. So if you have the limit of p of x, just again plug c in for all your polynomial functions. Rational is the same thing, plug in c. So basically you're just plugging and chugging. If you find that value, that will be your limit. So for this polynomial equation, we can just plug 2 in and see if we find that value. We get 18, and that's our limit. If it exists, has that value, that is the limit. Rational functions, same thing. Let's plug 2 in there and evaluate. So we have 18 over 6, which is 3, and that's our limit. Now, if the limit does not exist, if you find a value like -4, so we can do the same problem here. The limit as x approaches -4 for this function. Right away, I see an issue because I know I'm going to get an error, because if I plug -4 in for the denominator, I get a denominator of 0, which means I'm not going to be able to find that value. I'm going to error when I calculate that. So then I need to find values close to -4. So plug in values like -3.9, and then plug in values -3.99, and see what y values you get. Then plug values from the other side. Then plug in like -4.01 and -4.001, and see what these values are close to. Whatever the y values are approaching as you get closer and closer to -4 would be the limit. So even though this doesn't have substitution value, it would still have a value. So we plug in our values here, we get negative 2.9, negative 2.99, negative 3.01, negative 3.001 is the values we get. And so you can see that as we're getting closer and closer to our negative 4 value, so these values are closer and closer to negative 4, as these values are closer and closer to negative 4, we are approaching what number? We're approaching 3. And so 3 would actually be the limit of this. So even though it does not exist on x equals negative 4, the limit as x approaches negative 4 is 3. So again, as x gets closer and closer and closer to negative 4, our function here is getting closer and closer to 3. So that is the limit. Call it good for the night. We'll see you tomorrow.